Hello student, in today's lesson we are going to talk about the first theorem of isomorphism. Um, First of all, we have to talk about the objective of these lessons. First, to know that we can demonstrate or prove that many groups are isomorphism, and second, to know that exists groups that are equal but they differ in the name of their elements. You may ask, what is this? What is the first theorem of isomorphism? This is a theorem that we use to demonstrate the isomorphism of a group, and this was demonstrated by Amelia Amy Noether. She was born on March 23, 1882 on Germany. She was a German mathematician that made a lot of contribution to the abstract algebra. She was described by Pavel Alexandrov, Albert Einstein, David Hilbert as the most important woman in the mathematic history. Her father was the mathematician Max Noether. He motivated her or inspired her to study math and physics. She graduated from the University of Erlangen in Germany, and she later worked on the University of Göttingen in the Department of Mathematician with David Hilbert. She made a lot of contributions, and some of them are: she worked in the theories of algebraic invariant and the number fields. She proved the Noether theorem that explained the connection between the symmetry and the conservation law. That this theorem is used to prove the theorem of relativity, the Einstein. Third, she worked in theorism of ideals in community rings. She worked too in non-community rings and hypercomplex number. And finally, she proved the three theorems of isomorphic. In this lesson, we're gonna prove the first theorem of isomorphism. Let's start. The first theorem of isomorphism says that if we have a function phi that goes to g to h, and this function is a homomorphism, and we have another p function that goes to g mod the kernel phi, then exists a unique isomorphism phi that goes to the g kernel phi, go to the images of g that is a subgroup of h, such as that if we compose phi with pi that is equal to phi, we want to demonstrate that this phi function exists, that this isomorphism exists. We want to show that this group is isomorphic to the images of G. Like we said in this graphic, we take an element to G, and this element go to the image of G. We take the same element, this go to the G kernel phi, and we have this new function that go to G to the image of g. To show that this phi function exists, we have to go to 4 steps. First of all, to prove that this function is well defined. Second, to prove that this function is a homomorphism. Later, to prove that it's an isomorphism. And finally, that this function is unique. The uniqueness of this function. This is the function phi that goes to G mod the kernel of phi and go to the image of G that is a subgroup of Y, that what we said before, and is defined like this: phi x kernel of phi equal to the phi of x. Why like this? Because we take an element from this. We know that the element of this group is take an element of G and element of the kernel of phi. And we know that the image of phi, so their element is phi of x. And to prove that something is well defined, we have to take two elements from this group and say that these two elements are equal, and prove that their elements in the images is equal to. Let's take x kernel of phi is equal to y kernel of phi. This means that we have the same clauses but with different representatives, x and y. This means that the clause of x is equal to the clause of y, and by the definition of equal clauses, just means that x and the inverse of y is in the kernel. But what happens when an element is in the kernel? That means that phi of xy is equal to the identity in this group image of G by the definition of the kernel. And we can apply the homomorphism and say that phi of x, phi of y inverse equal to the identity of in this group, and we can multiply to the both sides by the phi of y. We have x phi of y inverse multiplied by phi inverse, and this is equal to the phi of y. And this concludes that phi of x is equal to the phi of y. But by the definition of this function, this is equal to phi x kernel of 5 and phi of y kernel of 5. And this is what we want to show. This means that this function is well defined. We show that phi is well defined. Let's show that is a homomorphism. We take two elements from this group and prove if the operation in this group is 2 in this group. Phi of x kernel of phi and another element y kernel of phi. We know by the operation of the clauses that is equal to phi of xy kernel of phi, and by the definition of the function that is equal to phi of xy, and we know this function is a homomorphism. we can split, and we know that is equal to this, and this is equal to x kernel of phi and phi of y kernel of phi. And this is what we want to show. We take two elements and the operation of the group is 2 in the image of G. And that means that this function is a homomorphism. The third thing that we have to prove, this function is a isomorphism. We know that to prove the function is a isomorphism, we have to prove that it's injective and surjective. And to show that it's injective, we have to show that the kernel of this function is unitary. We take the kernel of the function, the kernel of phi, that is equal to an element of y, kernel of phi, such as that this function with this element is equal to the identity in this group. But we know by the definition of this function, this is equal to phi of G equal to the identity. But we said by the definition of the kernel of this function, when an element goes to the identity, this means that this element is the kernel of phi. And that's it. We show that the kernel of phi is equal to the kernel of y, that is unitary. This means that this is injective. And to prove the surjection is too easy. It's take the same definition, because we know this element is surjective, and this means that this element is surjective too. That means that the function is surjective, and this is if the function is injective and surjective, that means this function is a isomorphism. And this means that this group is isomorphic to the images of G. We show that exists an isomorphism that goes to G kernel of phi, goes to the image of phi. That means that this group is isomorphic to the image of G. And the last step is to prove that this isomorphism is unique. Yeah, I'm gonna let you to prove that. It's pretty easy. It's take another phi prime, and to prove that phi prime is equal to phi. And that's it. And this is the demonstration of the first theorem of isomorphic. Let's see some example about this. Let's see this example. This example said we have a move function that goes to the C with the sum, goes to the Cm with the sum too, and we have a function defined that we have an element in C is equal to the class of the element, and we want to show that C mod NC is isomorphic to Cm. To show that, we have to prove that this function is a homomorphism, and prove that this element is the kernel of the function, and use the first isomorphic theorem and show that. Let's take two elements, A and Y, that is in C. If we apply the function A plus 1 plus B, This is equal to the clause of AB. Apply the definition of this. This is equal to A plus B. And what is this? This is mu A and mu of B. And this is the definition of homomorphism. We know that this is homomorphism. Let's see about the kernel. The kernel is pretty easy. The kernel of mu is equal the element that are in C. Let's see, take a L that are in C shows that the move of A is equal to the clause of 0. But because 0 is the identity in Cm. This means that all the element that is congruent to 0 mod n. N are element in Cm. But all the element that is congruent with n, this is MC. And like this, we show that the kernel of mu is equal to the MC. And using the first theory, the first theorem, that means that Cm and C is isomorphic to Cm, and that's it. This is the important about this theorem, that I can prove that we have two groups that are different but have the same structure. For example, this is used to prove that we have two C, the elements that are even, and C, and we know that these two groups have the same length or have the same quantity of elements in this group. And this is awesome because this revolutionary the algebra. Thank you, student. Let's prove you're gonna prove the uniqueness of the first theorem of isomorphic.